Okay, so let's get started. I hope the screen is visible to everyone. Okay, so coming to the first question that we have. So, which of the following is or are sufficient conditions to show isomorphism between two graphs G and H? So, first, what is isomorphism? So, if we recall, what is isomorphism? Isomorphism means, uh, can anyone say what do you mean by isomorphism?
So similar structure of the graph.
Yeah, you are right. So, same structure basically, not similar. Similar would be more general, but same structure. So, some common examples of isomorphism would basically look something like this. So, let's say you have this star shaped graph. So, you have uh, five vertices, and these are the edges. And this is isomorphic to a pentagon. So, these are isomorphic. Now, if you look at these two graphs, what is common in them? So, one, same n- number of vertices. Number two, same number of edges. And number three is the degree sequence. So you'll notice that they have the same degree sequence. So what I mean by degree sequence is if you write down the degree of this graph, let's say, so it is 2, 2, 2, 2, 2. Same here also 2, 2, 2, 2, 2. So here, for example, the degree sequence is 2, 2, 2, 2. So you see, these are isomorph. But what do you think? These conditions, are they sufficient? So in our questions, they have asked what are the sufficient conditions. So do you think that if these three conditions are met, the graph will be isomorphic, or do you disagree? Anyone? So my question is like this. So are they necessary or sufficient? What do you think? These three conditions, are they necessary or sufficient conditions? Anyone? So, by necessary conditions, I mean is that if these conditions are true, then uh, means these conditions have to be met for the graph to be isomorphic. But if these conditions are met, it need not be that the graph is isomorphic. So, uh, and sufficient conditions are that if these conditions are true, then it implies that the graph is isomorphic. So, what do you think? These are necessary or sufficient conditions? So, these are actually necessary condition, not sufficient, because we have a counter example. So, I can give you a counter example like this. So, like I said, this star and pentagon are isomorphic, but if you put them inside another uh, big pentagon. So you have one, two, three, four, five. So if you take like this and you take so what do you think? Are these two graphs isomorphic? So they are not isomorphic. So not isomorphic. Even if all conditions satisfied. So w- what is the test for isomorphism is basically isomorphism. You have one, you a bijection between uh, vertex sets and two presence of associated edges in both graphs. What do I mean a bijection? Bijection is a one-to-one mapping. So you have, let's say, consider the first example. So you have, let's say, I call this as A, B, C, D, E, and I call this as 1, 2, 3, 4, 5. So the bijection says that you have A, B, C, D, E. You can map it to 1, 2, 3, 4, 5. So how the mapping looks like that A is mapped to 1, B to 2, C to 3, D to 4, and E to 5. So this is a bijection. So it is both a 1 1 and an onto function. So this is a bijection and presence of associated edges. So in the left set, you see that uh, okay, so this is actually the bijection that I have drawn is not correct. So I'll uh, so this is a you can say this is one bijection, but this bijection uh, m- does not satisfy the second condition. So presence of associated edges in both the graphs. So if you see in graph on the left graph, the star graph, A is connected to D and C. So that should mean that 1 should be connected to 3 and 4, but 1 is connected to 5 and 2. So the corresponding associated edges, so in the left hand set, since A is connected to D and C, 1 should also be connected to 3 and 4. So that would be a valid mapping, but this is not. So how to change it? So we'll change the bijection a little. So like if you observe, A is connected to D and C. So basically you so I'll draw this figure like this. So you have A and you have uh, you connect it to D. You have A, you have D, and you have C. C is connected to E. C is connected to E and A. So I draw E over here. So and D is connected to B and A. So I'll draw B over here. So now if you join this, this is the pentagon to which it is mapped. So now you compare that what sits at A, 1. So let's say A is connected to 1, and we have this other graph. So like this. So it is 1, 2, 3, 4, 5. So C goes to 2, E goes to 3, B goes to 4, and D goes to 5. So this is the now both the conditions are met. So it should be a bijection and the presence of associated edges in both the graph. So this is the correct bijection. So this is one way of checking. But if you see the given statement, so we have four questions. So four options that the graphs have equal number of vertices, they have equal number of edges, and the same degree sequence. So these three are necessary, not sufficient. But this one, complement of G and complement of H, this one is actually the sufficient condition. So they are isomorphic. So this statement 4, you can prove it by taking these uh, by taking the this definition of isomorphism, that a bijection should exist and the presence of associated edges in both the graph. So the uh, if this is isomorph, if the uh, if their complements are isomorphic, in which case their the complementary graphs the of G and H will also show a bijection. So what is the complementary graph would look like? So it would look something like this. So the complement would look like this. So actually the if we draw the complement is all the edges that are not present in the this edge in this graph. So the complement of so the outside edges won't exist. So you will have five vertices, but you will have all the inner edges. So this is the complement. And similarly, the complement for this graph will also look like a star. So now the complement set is also a bijection. If you see A, B, C, D, E, and 1, 2, 3, 4, 5. Now see again, uh, you have A matches to 1, C to 2, C to 2, um, and E to 3, D to 4 and D to 5. So you see the mapping still remains the same in same mapping, but the complementary, so uh, both are bijections and the associated edges would be present, and hence this is the actual test for isomorphism. The complement of G and complement of H should be isomorphic. I hope this is clear to you. Okay, uh, let us move on to the next question. So a graph G has 6 vertices and 10 edges. What is the sum of degrees of all the vertices in G complement? So basically, if a graph has 6 vertices and 10 edges, so what is, in consider K6, the complete graph with 6 vertices. So number of edges in this graph would be anyone. What is the total number of edges in a K6 graph?
6 choose 2.
Right. So it is 6 choose 2. That would be 6 into 5 over 2. That is 15. Now it is said that G in G number of edges is equal to 10. So what is the number of edges in G complement? So G complement consists of all the edges that are absent in G and no edge that is present in G. So basically it is the number of edges of K6 minus number of edges of G. So this will give you the number of edges of G complement. So that is basically 15 minus 10, that is 5. So uh, this is the number of edges that are present. So they are asking what is the sum of degrees. Sum of degrees is nothing but twice the number of edges. So twice into the edge, 5 is 10. So option C is the right answer for this question. All right. So let us move on to the next question. Is having zero odd cycles a necessary condition for a graph to be bipartite or a sufficient condition? So you see that a bipartite graph is can be divided into two sets basically. So you have one set over here and another set over here. So a bipartite graph will have uh, connections across the sets. So it can be connected this, like this. So you have this set U and this set V connections across UV. So this is true, but no connections within U or within V. So the second one cannot hold, so you have connections only across U and V. So this is a bipartite. Now they are asking us whether uh, having zero odd cycle. So what does the odd cycle mean? So let's say it is Cn. So where they are talking about n is odd or even. So this is what is meant by odd cycle. So basically you have a this is a odd cycle. So let's say this pentagon. So this is a C5. So this is odd. So this is a odd cycle, but uh, this one is a even cycle. C4, even cycle. So you have two categories of cycles. Now, is it a necessary condition for a graph to be by to have zero odd cycles? So which means that so what does this odd cycle refer to? So it basically means that uh, so first an odd cycle would comprise of mapping going from U to V and back to U. So, so like, and obviously it has to be uh, complete. So for the cycle to be complete, so it would be, so you have come to, so like this, I'll show you an example. So it would be something like this. So U V back to you, but this is not a cycle. To complete the cycle, this one should also be present. So uh, this is not a cycle. To but consider this, you have one on U, another on V, another on U, you go back to V and back to U. This is a cycle because you came back to the same point you started. So if you see the cycle to be complete, you cannot end at U. It uh, has to, uh, in this case, it is U, V, U, V, U. So this is a complete cycle, but this one is a odd cycle and it cannot be complete. So you see that it has to be even cycle for a bipartite graph. So the right answer for this question is it is both necessary and sufficient. So if it is a, now we have shown you the necessary part. So for the sufficient part, you basically take any cycle and you can split the cycle, like, since a cycle can, what is the chromatic number of a cycle? It's either 2 or 3. So you can just like in an even cycle, what is the chromatic number? So for a even cycle, can anyone tell me what is the, let me write the question. So for an even cycle, what is chromatic number? Like, how many colors do you need to color the cycle so that no two adjacent edges are of the same color? For an even cycle, what do you think is the chromatic number?
Sir, 2.
Right. So what does this mean? That you can split it up into two colors. So if you take, let's say this, I'll take a big 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 vertices. 1, 2, 3, 4, 5, 6, 7. Yeah. So now I can color it in two different colors. So let's say I color it red. I alternately color it red, and the other one I color it green. So basically, what does this mean? That I can put one uh, green set, and I have four elements in this green set, and I can create a red set. So, and then there is a bipartite. So every red is connected to two green. So so let's say I name them 1, 2, 3, 4, 5, 6, 7, 8. So let's say 1, 3, 5, and 7 I put in the red camp, and in the green I have 2, 4, 6, and 8. So I can draw a connections from 1 between 2 and 8. So 1 is connected to 2 and 1 is connected to 8. Similarly, 3 is connected to 2 and 4. So 3 goes to 2 and 3 goes to 4. And 4 is connected to 3 and 5. 5 is connected to 4 and 6. So you have 4 and you have 6. Similarly, 7 is connected to 6 and 8. 6 and 8. So this is the bipartite matching. So it is both necessary and sufficient. Necessary because I showed you like that if it is an odd, you cannot form a bipartite. So in a if it is odd, then it need not uh, form it can be bipart it cannot create a bipartite graph. So like in this odd cycle, so it cannot exist in a bipartite graph. And if you have been given an even cycle, then you will always uh, you can always create a bipartite graph. So that's why it is both necessary and sufficient. So the answer is therefore option C. Okay. uh, Coming to question 4. So, given a degree sequence, so you have this degree sequence where 3, 3, 3, 3, 3. So, choose the correct statement from this option. So, such a graph is not possible. Such a graph is possible, but it won't be Eulerian. Such a graph is possible and will be Eulerian. So, to answer the first question, so given this degree sequence, is this graph possible to make? Is this graph possible to make? So basically, we'll have to answer this question, that is the degree sequence graphic or not? So if it is graphic, then we can create a degree sequence. If it is not, we cannot. So what do you think, that given this degree sequence, what do you think? Is it whether it can be graphic or not? Just taking a look at it, can anyone say whether it is graphic or not, the degree sequence? So how many uh, nodes are there? So you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 nodes, and they are saying it is a regular graph with each vertex having uh, three a degree of 3. So what do you think? Is it a graphic? Can it be a graphic degree sequence or not? If you recall the handshaking lemma, shaking lemma, so what it says, that even number of odd degrees, even number of odd degrees. Now, So in this graph, we have 8 nodes having odd degree, which is 3. So by handshaking lemma, we can say that this graph is possible to make because we have even number of odd degrees. Now, whether this graph will be Eulerian or not. So can anyone tell me what is an Eulerian graph? So I'll ask this question. What is a Eulerian? What is a Eulerian graph?
So traverse all the edges of the graph without repeating the edge twice and starting from the same vertex and ending over there.
Right. So it's basically a circuit that covers all edges exactly once, not more than once. So this is an Eulerian graph. So what is the litmus test for Eulerian graph? So what is the litmus test? How do you know a graph is Eulerian or not?
Degree of all the vertices has to be even.
Exactly. So degree of all vertices is even. Now you see this degree sequence, it is odd. So all the degrees are odd. So it cannot be Eulerian. So the right answer is that such a graph is possible, but it won't be Eulerian because by the handshaking lemma there are even number of odd degrees. So the graph is possible, it is graphic, and but it won't be Eulerian because the degrees are odd. For Eulerian it has to be even. So uh, option B is the right answer. So let us move on to the next question. Which of the following statements is or are true? So if a graph is Eulerian, it will always be Hamiltonian. If a graph is Hamiltonian, it will always be Eulerian. If a graph can be both Eulerian and Hamiltonian, or option D, there is no certain relationship between a graph being Hamiltonian or Eulerian. So, like we discussed, what is Eulerian? Just to recap, what is a Hamiltonian graph? So, can anyone just recap what a Hamiltonian graph is?
So a cycle that traverses all the vertices of the graph.
Right. So it is a cycle that traverses all the vertices exactly once. So in Eulerian, it was the edge, and in cycle, it is the vertices. So in the oil, so these two may look very similar, but they are not the same problem. So the right answer for such a question is that there is actually no certain relationship between a graph being Hamiltonian and Eulerian. So we have a definite litmus test for a graph to be Eulerian. So it is a necessary and sufficient condition. So degree of all the vertices should be even. This is necessary and sufficient. But for Hamiltonian graphs, we have sufficient conditions such as Dirac's theorems and Ores theorem, but no definite necessary conditions. And a graph can be Hamiltonian and uh, so I'll give you some examples. So where the graph is Hamiltonian and Eulerian both. So if you take this cycle, so this is both Hamiltonian and Eulerian. So you can traverse all the edges once, you can traverse all the vertices once. But if I just uh, put one edge in between, if I put this edge, this is still Hamiltonian. Hamiltonian I'll write by H, but not E, because you cannot traverse through this middle edge without traversing through one of the other edges more than one. So this is because this degree of these two nodes have become odd. So you need even degree. So this is not Eulerian. And similarly, you can have Eulerian graphs as well, which are not Hamiltonian. So it depends on the particular graph in question. So uh, in so it we cannot just tell whether a graph is Hamiltonian or Eulerian. So it has there is no definite rule. We have to check for the given graph. Select the correct statements from the option given below. So Dirac's theorem is a generalization of Ore's theorem. Ore's theorem is a generalization of Dirac's theorem, and neither Dirac's theorem is a generalization of Ore's theorem, nor is Ore's theorem a generalization of Dirac's theorem. So, like I mentioned, so let us recall what is Dirac's theorem. Dirac's theorem is that every node has degree greater than equal to n by 2. So n is the number of nodes in the graph. So this will ensures that graph is Hamiltonian. And Ore's theorem says that any pair of node u comma v, let's say from the graph. So degree of u plus degree of v should be greater than n, then graph is Hamiltonian. So what do you think? Which is the more general statement? Anyone out of these two theorems, which do you think is the more general theorem?
Sir, I think Ore's theorem.
Right. So Ore's theorem considers this case. So if you so it is basically like this. So Ore's theorem is a bigger set, and within which you have this uh, Dirac's theorem. So in Ore's theorem, you have cases like it could be 1 plus n minus 1, and still you can say that the graph is Hamiltonian. So it can exist. But in Dirac's theorem, it has to be more than n by 2 and n by 2. So only such special cases are considered in this Dirac's theorem. So Ore's theorem is the this is Ore's and this is Dirac. So this is Ore's theorem covers a greater range of options than Dirac's theorem. So this is option B. Ore's theorem is a generalization of Dirac's theorem. In coming to question 7, a complete bipartite graph is one in which all the vertices of one set are connected to all the vertices of other set. So we assume that in the two sets, the elements are m and n, and they are greater than 1. Which of the following is the sufficient condition for the graph to be Hamiltonian? So we have again, like I drew, so we have, let's say, yeah, m elements and you have n elements. Now in complete graph, complete bipartite, every element in this one set is connected to all the elements in the second set. So let us call this set A and B. So every element from A is connected to every element of B. So what is the degree of any element in A? Degree of, so let us say, so degree of any element in A. What do you think is the degree of any element in A if it is a complete bipartite graph? So degree is the number
N.
of n, right? So it is because it is connected to all the elements in B and B has n elements. And similarly, what is the degree of any element in B?
M.
Right. So now for if you recall Dirac's law, so let me write. So total nodes equal to m plus n. Now by Dirac's theorem, n should be greater than equal to m plus n by 2 and m should be greater than m plus n by 2. So this is your total number of nodes m plus n, and so every element in B should have degree greater than the total elements, half of the total number of elements, and similarly every element in A should have degree more than half the total number of elements. So from here you get n should be greater than equal to m, and here you get m should be greater than equal to n. So combining these two we get m equals to n. So the right answer for this question is option A, m equal to n. I hope that is clear to everyone. It's just simple algebra and use Dirac's theorem in between. So you get m equal to n. Okay. Uh, Coming to the eighth question, a, c- a K5 is a complete graph on 5 vertices. So what is the smallest number of edges that you need to delete from it to make it planar? So I will, so what is a planar graph first of all? What is a planar graph? Can anyone say what is a planar graph? Anyone? So planar graph is a graph where edges do not intersect. So this graph, if I draw, this is not planar because here it is the edges are intersecting. But the same graph I can draw. So let's say these are the vertices. I can draw the same graph in a planar fashion as well. So you have the 4 vertices. So they are connected among themselves and one of them goes inside, but the other one goes from outside. This is planar. Okay. So I hope what The definition of planar graph is clear to you all. So now let us look at what is the smallest number of edges that you need to delete from a K5 to make it planar. So first I'll draw K5. So you have 5 vertices, 4, 5, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is your K5. So obviously it is not planar. A complete graph is actually never planar. So I think it is the proof was discussed in the lectures as well. So now we'll have to remove some edges to make it planar. Let's see how we can do. So what we do is we keep the outside edges first. We keep them. For the inside, we see. Uh, so we have one. So the points of uh, intersections are these. So these one, we have 5 intersections. So let's say I take one of the edges out. So I named it with one. That is 1, 2, 3, 4, 5. Is 1, 2, 3, 4, 5. Now I take out this edge 1, 4 from outside. Okay, so I kept 2, 5 inside, 1, 4 outside. So now I have left with 5, 3 and uh, 2, 5. So now let's say I draw 2, 4. I draw the 2, 4 inside. So still no intersection. But now I am left with only one. Uh, so 1, 3 again I can take it from outside. 1, 3. So the remaining is this 5, 3 node. So the 5, 3 edge, if I just remove, I don't keep the 5, 3 edge, then what I get is this, a planar graph. So this is planar, no intersection as you can see. So how many edges I removed? Edges removed equal to 1. Which edge? That is the 3, 5 edge. So the right answer for this question is D. So only one edge can be, if we remove only one edge from K5, it would become a planar graph. Coming to the next question, 9. So let M be the chromatic number of a bipartite graph and N be the chromatic number of C3. So in a bipartite graph, we have already discussed that a chromatic number of a bipartite graph is 2. So M equal to 2, there is no doubt. Now, what is the chromatic number of C3? So C3 is basically you have a cycle with 3 elements. So how many colors do I need for to color them? So if I color it with blue, I color it with green, I'll have to pick a different color. So since it is a odd cycle, we'll have 3. So a odd cycle has chromatic number 3 and an even cycle has chromatic number 2. So n equal to 2. So now what are the sorry, n equal to 3. For even it is odd cycle and n equal to 2 for even cycle. So which options are correct? So you see that m is less than n and m equal to n minus 1. So both of them are correct. So option C and D are right answers for this question. So this is a pretty straightforward question. So coming to the final questions for our discussion. So you are given a planar graph. You are certain to find at least one edge. So it should won't be edge, it would be one node with degree at most 5. So what it means is that the degree sequence, so it means that there exists a node with degree less than equal to 5. So to prove it, whether it's true or false, we'll prove it by contradiction. So we contradict this statement. So proof by contradiction. Okay. So so the we assume that this statement is false, which means that what is the if the negation of this statement, this the negation of this statement means that all nodes have degree. So this is we are assuming let all nodes have degree greater than equal to 6. So you have n node. So sum of degree would be equal to 6n. Now, what is if there are e edges? So are e edges, it means that uh, sum of degree so equal to 2e. So this sum of degree would be greater than equal to 6 and 6 because all nodes have degree greater than 6. And if there are e edges, the sum of degree is twice the number of edges. So that is 2e. So basically 2e is greater than 6n. So e greater than equal to 3n. Now, but for planar graphs, e less than equal to 3n minus 6. So this inequality comes from this VE minus R, V minus E plus R equals to 2, and this 2R, sorry, 3R less than 2E. So these two conditions, if you put in this, you get this condition that E less than equal to 3n minus 6. So you have one condition where 3n is E is greater than 3n, but another condition that says that E is less than 3n minus 6. So it is like this. So you have this is So you have this is 3n minus 6 and this is 3n. So the first condition, so I'll color it in red. Right. So this is red and color it green. So the green condition says that E should be somewhere here. And the red condition says that E should be somewhere here, but it cannot simultaneously be above 3n and less than 3n minus 6. So this gives rise to a contradiction. So we assume that this statement was false, that there exists a node with degree less than equal to 5. So there exists uh, at least. So this was our, so we took the contradiction of this statement and tried to find that whether this, the contradiction holds, the uh, negation of this statement holds true or not. We find that the negation of this statement does not hold true. So, which means that this statement must be true. So, the right answer is option A. So, here we proved that negation of this statement is false. So, the statement itself must be true. Therefore, the right answer is option A. So you'll always find a node with degree less than equal to 5 in a planar graph. So that brings us to the end of our discussion. So if you have any doubts regarding the questions I have discussed, you can ask.
Sir, I have doubt in question 3.
Okay, wait. Yeah, go ahead. Yeah,
Sir, in checking the sufficient condition, so if the bipartite, so if the graph has zero odd cycle, can it mean that it can have no cycle at all? It can have even cycles, but it can
yeah,
also mean that it will have no cycles at all.
yeah,
So in that case, will it be bipartite?
yeah, definitely. So zero odd cycle is basically this graph. So you take this. So let's say I have two elements. So this graph doesn't have any cycle. So this is a still a bipartite graph. So zero odd cycles, zero cycles basically. So neither odd nor even cycle. But if you have the same graph, you take like this, and you can connect this cross edges. So it has one cycle. So this is a 4 cycle, C4. So it's a one even cycle it has. Is it clear?
Yes, sir.
Yeah.
And sir, in the next question, so
Yeah.
is the handshaking lemma a sufficient condition? Cause in previous lectures, when we were checking is graphic, we were
Yeah.
checking with Havel Hikimi when it.
Yeah. So this is not actually, and so it is possible. So it's not by possible, it is not guaranteed. So like it means that it is, it may be possible, but if it is uh, not, it is basically, handshaking lemma is basically a necessary condition. So it has to hold true for a graphic degree sequence to exist, but it does not make the a sequence graphic. So by possible, it is not meant guaranteed. So you'll have to do that Havel Hakimi algorithm check to find whether it is graphic or not.
Oh,
So,
okay, sir. Thank you.
yeah, so this is necessary. Any other questions?
No, sir.
Uh, all right then. So if no one has any other questions, we can close the session for today and we'll meet again next week at the same times. So all the best for the course and see you again next week.